Ladies and gentlemen, please welcome Eric Horvitz, Distinguished Scientist and Deputy Managing Director at Microsoft Research.
Well, good morning. We're certainly having some exciting times these days with what's happened over the last, let's say, 25 years in the amount of computation and memory we have at our fingertips. The incredibly unexpected connectivity and data, from my point of view, putting myself in my grad student shoes in the 80s. And potentially most of all, and stunning and interesting, I think, are the advances in our ability to learn and reason from data, as well as to do perceptual things, to listen, to observe, to recognize with vision systems and acoustical systems these days. Lots of opportunities and directions come from these advances, and they're only increasing. And I think right now we've gone superlinear. I mean, things are, for a while we were, I would say, sublinear in AI, artificial intelligence, but we're moving quickly at a fast pace. And things are accelerating, and it's very exciting for somebody like myself and my colleagues who've been struggling for many, many years in this field on the dream of AI. I wanted to just start a little bit up with some background. In the 1980s, you might say there was a kind of a revolution in artificial intelligence when we started as a community looking very carefully, in some ways rediscovering probability and utility and decision theory. For many years, AI had gone into the world of logic-based systems, logic reasoning, which is fabulous work and theorem proving and so on, shunning the notion of uncertainty in many ways. In the 80s, there was a rediscovery of this methodology. And what you see here is a Bayesian model or Bayesian network that we created on my team at Stanford in 1985, 86 or so. What you see here, those nodes are variables. These are variables or observations you might capture in an intensive care unit at a hospital. Up on top here, if I can grab the mouse, if I have a mouse that's moving here. Well, anyway, up at top are causes, things you worry about with illness and physiology in an intensive care unit. In the middle are unobserved variables you can't see very well, like catecholamine levels. And at the bottom are observables. And the idea is methods were developed to take any subset of observations you might see, like heart rate and blood pressure, and propagate that information through these models to give us probabilities of things we cared about and make decisions based on that. Now, in the old days, we didn't have very much data, so we would build these by hand, sitting with an expert for days and days, it would turn out. In the latter 80s and into the 90s, the community developed a number of methods that could take large amounts of data, because we actually began having access to this data, and developing procedures for learning those kinds of models, let's say for 3 variables here, and structure, that could be used to make predictions in the world with procedures like searching through a space of models and finding the model that best explained the data here you see in the, with the red there, circled there. And those models can be used not just for making, for inferring hidden states of the world, like the intention of a user, for example, entering a query, or a particular disease process active in a patient, or what the state of traffic will be on 5 north in 2 hours, but also could go from these predictions to actions in the world by embedding them in what's called a decision model that balances the costs and benefits of action under uncertainty. So we look at this interesting pipeline, data to predictions to decisions, as being critical both in business and in consumer applications of a variety of kinds. The advances you've already been seeing and touching daily in search and advertising online, in recommender systems that tell you which book you might buy given the books you've already purchased and so on. Just a few years ago, those applications, when we developed them at Microsoft in the early 90s when I first started here at Research, were considered quite exotic. I would show people a recommender system and say, look at this toy site using Commerce Server 2.0 with our new technology we call collaborative filtering. Watch what happens when someone surfs the web and they look at these toys on this toy site. Look at these toys being recommended, and people would applaud in the audience. This was an exotic concept. Now, our aunts and uncles are daily working with the web and dealing with recommendation engines and so on. Beyond search and online services, though, we're seeing quite a bit of activity and advancement in speech, natural language, gesture recognition, as you see from our offerings like the Connect other kinds of applications coming out around that, and there are advances going on that front. But newer applications coming to the fore in terms of recognizing activities that you would think only people would recognize from a distance, for example. Deeper understanding of the intentions and goals of people working with software or walking in the world, if for example, emitting GPS signals with their permission, understanding what's going on in one's life, their mood, even understanding cognition. If we have some time today, I'll talk about some work in the models of human cognition space. But in some core work in transportation and healthcare and the environment, we're seeing some interesting innovations. And I want to talk about a couple of case studies today, give you a sense for the end-to-end of some of this research in some sort of easy-to-understand applications like traffic flow and healthcare. And then we'll spend a little bit of time towards the end of the presentation on what we call integrative AI. As opposed to trying to do monolithic efforts in vision or speech, there's been an interesting trend, and we have some sister groups at universities around the world. We have a close sister group at Stanford University, where we take parts of the best of breed of work in different areas of AI, like vision and speech and activity recognition, and planning and robotics, and weave these components together to see if we can get more than the parts in a whole, and even understand what it takes to build new kinds of integrative experiences and intelligences from components. And we're seeing these kinds of things become ready for daily life. Let me start with a case study in transportation that gives you a sense for how tech transfer works at Microsoft. And the experience we had. So I don't know where everybody comes from here, but I can guarantee you, even being a person that was at Stanford in the Bay Area for many years, where traffic was horrendous, that no place is worse than Seattle. Well, we all sort of have our pet cities for complaints about traffic. And so it was just on our team, we had expertise in machine learning, and we thought, back in this is basically around 2003 or so, he said, can't we take the traffic we're getting, the feeds we're getting from the Seattle highway system, the little, red, yellow, and green dashes and dots you see on the highway that's being sensed by the traffic department. Combine that with incident reports. This is a telegraphic report, kind of like very brief, but sort of a natural language about what's going on different aspects of the highway system with accidents. Weather feeds were now available. We had major event schedules like Mariners games in Seattle. And the idea of combining these heterogeneous streams into a single database and then saying, let's actually take a big database of like 4 years of data and now build models that for any segment on the highway system could predict the flow in the future, not now, but if I'm planning on leaving in an hour, for example, what's going to happen. And we built a little app called SmartFlow in those days and distributed it at Microsoft. That's a green disk there you see. Let me go to the red one here. Those little clocks appearing by the arterial system are visualizations of how many minutes until the clog melts. So you see here 10 minutes on the right side, 30 minutes in the middle there. The green meant how long it would stay open until a clog. And we were very excited because we could also distribute this on smartphones. We offered that the system would actually give you the maximum time the bottleneck would last, as well as the standard deviation. You should have a sense for the error, the system's own confidence in its inferences. Now, we actually then start thinking about, wow, how do people actually use devices in the real world? Well, most people in Seattle fashion themselves as traffic experts. So we thought about this. When should a device come forward and buzz you? And this led to a whole research project in itself on what's called user modeling, which is going to be it's a more and more important area in the machine learning space to understand users deeply. So in this case, we said we have a system with a world model. In this case, a traffic system understands it can predict the future of traffic over the next hour, for example, in different parts of the highway system. That's running, we'll call it the world model. And it's generating probability distributions, looking like a little histogram here. It's never really totally certain, but it has an idea. Here's a human being, let's say the semi-expert, experienced person in Seattle who knows the traffic system on the way home, looks outside, it's raining out and so on, knows time of day and day of week, and he or she has their own probability distribution about what's going to happen. And what we thought would be interesting is if we actually could give our systems knowledge of a user model that would explain what people might think. There it is, we're guessing now, and together reason about when is it important to tell somebody something that they don't know, which is an interesting direction, I think, for AI. We call that complementary computing. How can I compute in a way that takes into consideration the way people think? Now, here's what we did with the traffic system. We call this a model of surprise. So basically, our system understands, people understand major events, weather, time of day, day, week, and holiday status. And there's a real-world outcome here. We can actually take 15-minute sections of time for every street segment on the highway system in Seattle, and by time of day and day of week, and get a sense for what's expected. And then look at outliers, flows where you wouldn't expect them, like it's jammed. It's jam-packed at 2 p.m. on Sunday afternoon in a place that's never that never sees traffic, or it's slow. It's fast going tonight in the rain on 405 North during rush hour, which should be unexpected. And the idea is to take these human surprises and create a data store. We're learning at a different level now. We're learning what events would surprise people, and looking at the time of day and day of week, and looking at everything the system can see, which is a lot bigger picture than people see, including the history, the traffic accidents, the flow of clogs through the system. There's a dynamism there. But even more interestingly, we said, let's go back in time, let's say 30 minutes, and look at what was happening before the surprise occurred, such that if I could make an inference, we can build a model with machine learning that might give us what we call a surprise forecasting model. This basically tells us that people will be surprised in 30 minutes when they're not even surprised now. So this is a little symbol of saying the system knows that you, the commuter, are surprised about this delay. This over here means that you will be blown away that in 30 minutes, this area of 405 North near the Wimbledon Tunnel is wide open. So the system is actually understands people now, and it's coming forward and buzzing them and so on. And people on the way home, they can actually, on a desktop computer, set up their commutes, their AM commute and PM commute, and just tell the system, only let me know when I'll be surprised by a clog on my route on my way home in 30 minutes. So that was Smart Flow, and it was quite successful. We had several thousand users internally at Microsoft when we first put this out. We logged them by contract, so we understood how it was working and so on. And then one day I was driving along on the highway system, heading 405 North. I had my in-laws here. We were taking them to a vegetarian restaurant we hadn't been to before. And we were just all of a sudden stuck in traffic on the highway. And I said, that's interesting, so stuck. I have a GPS system in my car. I'll go on the side streets. I can route around this traffic. Well, it was even worse. The side streets were worse. And most context-sensitive traffic systems assume, highway clogged, I'll take that offline, and side streets are smooth and flowing at speed limit. They don't realize that we have to consider the holism of traffic in a city area. So we had this grand challenge. We said, okay, in most cities, big cities in the world these days, at least in North America, we sense the major arterials, the highway system. But we really need to know all streets, all surface streets, plus the highway system to route effectively through traffic. So the grand challenge to my team was, can we make the complete highway, the sensed highway system, a mega sensor for all traffic in a region, understanding the properties of the road and the weather and other contextual features? If you could, you can do routing with one of these search algorithms called Dijkstra or A*. The searches we depend on in our GPS systems these days, in our cars and in our pockets. You can do that effectively. And so we set off on our moon mission to see if we can do this with road topology, big maps of the highway and surface street systems, weather, time of day, and so on. And to do this well, we needed to basically go out and get data. So we had highway data for 4 years. we ended up in those days handing out GPS devices. These weren't ubiquitous on phones yet at the time. And we said to Microsoft employees and their spouses volunteering, drive around Seattle. Just take it for a while. And we had about 1 million kilometers, 100,000 trips when we started doing our data mining. And the idea was, can I learn the personalities of street segments I haven't even seen before with this model from data that I have that joins together the highway flows with the surface street flows. This shows you a little bit of the model here. It's a little hard to see here right now, but in general, we have different types of relationships. We have databases that tell us about how roads join together, how they flow. For example, how far away is a current surface street from a clogged on-ramp to a freeway in routing distance. Computed real-time relationships and so on. And this led to a prototype we call ClearFlow. Now, ClearFlow we let out internally at Microsoft. We told Craig Mundy and Bill Gates, all of our colleagues, go use this, and we watched how well these things worked. And the system worked, ClearFlow. And people, this is an example of how it works. So you basically say, where you're going, when are you leaving, and the system would actually go out and show you the traffic. And it even ran in this kind of mode where it would show you, we weren't really wanted to do a A/B Pepsi Coke comparison. So we would show on the left the ClearFlow directions and timing estimates, and then at the time map point, the default. And even showed how each one thought about the other's routes. It was kind of interesting to watch. So users could inspect and play with the experimental aspects of the system. See on the left, ClearFlow is saying get off the freeway going north and get on the surface streets, while MapPoint says stay on the highway system. The system worked quite well. We formed a virtual team with the product group over at Bing Maps. And within a year and a half, we fielded ClearFlow across North America to 72 cities. So now if you have a Windows phone, this is the default inference. You can also get it on maps.bing.com if you've resisted buying a Windows phone. The basic idea here is that it's reasoning. Every few minutes we assign road speeds to over 60 million street segments across North America with these probabilistic models learned with machine learning. What's kind of fun about it is like a few months ago when we first went onto the Windows phone, one of the research engineers on my team, actually the Jason team, came up to me and he mentioned, boy, this is discovering my secrets. I'm not sure I want to give these away, where I get off the freeway and go around and get back on again. And ClearFlow is figuring all this out. So it's like, it's like doing this. We'll see how that goes as more and more users use the system and it continues to learn to adapt. But it was a big success story for us in actually getting one of the largest applications of machine learning out in the world and in the hands of users today. For a while, when it first came out, it was called ClearFlow on Bing Maps. Now it's just called traffic-sensitive routing. Here's an example of on the Bing Maps here. A key decision you make in Seattle quite often is, do I take the bridge, and if so, which one? And secondarily, do I go around the top in Seattle to go from the east side to Seattle? And this is an example of one day here where it says, oh, here's the best route without traffic, 15 miles, 24 minutes, but 50 minutes coming from ClearFlow estimates in current traffic conditions. And if you click on see best route based on traffic, it says, I know this is counterintuitive, but go over the top. And that basically will be 35 minutes. And it's basically computing that. That would never be faster if you had good traffic. But you need to actually know how fast that is going as well. And we're doing inferences across the whole road network in Seattle. Let me now go from that case study to one in healthcare, give you a similar kind of sense for another project that's moving from kind of, you might say, daily nuisances of getting from here to there to some very, very high stakes and critical problems in healthcare. So we've looked at several problems in the healthcare area, one of which is the challenge of reducing hospital readmissions, where a patient will be discharged from a hospital, and then by definition these days, within 30 days, is readmitted to the hospital with the same problem. This has been a hot potato. It's been in in the political world, people talk about, well, this is a sign that our medical system really needs to be fixed. A couple of years ago, an article in the New England Journal of Medicine analyzed data from 2004, and they found from that Medicare data that 20% of patients were bouncing back within 30 days of discharge from the hospital, and 35% within 90 days. If you believe these bounce backs are preventable, which is actually another question we can ask, the estimated cost to Medicare that year was almost $17.5 billion for the bounce back, the care for the bounce back. So we basically got involved working with a hospital in Washington, D.C. area, and very closely with that team. It's one of the top 10 urban hospitals in the United States. They've done a remarkable job of collecting data for over a decade. And as an example, they had data on 300,000 emergency department ED visits. And the data is very, very detailed. Admissions, discharge, transfer, chief complaint, free text, age and gender, diagnostic codes, even labs and results, medications, vital signs, procedures, even rooms people were in as they moved around the hospital, fees and billing. About 25,000 variables are in this data set. It's a large data set. We asked the question, can I build a model with the method I talked about before, search through this space, given the data with a machine learning algorithm, and build a predictive model that could predict, for example, in this case, EDA. Patient is discharged from the emergency department and bounces back within 2 weeks. And the variables lighting up are the variables we find are the indicators. They help us understand its gender, its diagnostic codes, how many hours in the hospital, age, and so on. Or, for example, bounce back within 30 days and understand that. Beyond this predictive model, we can actually run the predictive model. The way you do this is you say, I'm going to train up a classifier or a predictive model from data with a machine learning algorithm from 80% of the data, often the first 80%. And then for the last 20%, I'm going to hold it out from the machine learning algorithm. It's not going to see it. In fact, to the classifier or the automatic method we build from the machine learning, we're going to make believe the 20% that hasn't seen yet are new patients coming in, to give us a sense for how it's going to work in the real world. And that's what we mean by this train and test. We hold out some test set there, and then we actually see how well it works. And we often build, in many fields of machine learning, curves like this. What you see here is the false positive rate at the x-axis and the true positive rate. And you can sort of pick a threshold and operate at different points on this curve. For example, a hospital might say, okay, I like this point here. I want to basically capture all the patients, or 3/4 of the patients on the y-axis there, 75% or so, who will bounce back within 30 days. I realize, because nothing's perfect, I'm going to tolerate a 25% false positive rate, people that wouldn't have bounced back, but they still are flagged as risky patients. The other thing you get, besides a runtime classifier that you can use, is you can look at the data here, and the systems will tell us, these algorithms, what are the important variables. So, for example, you might say, okay, in the emergency department, we do see many pregnant women who are vomiting and they come in, they're nauseous. That's a common occurrence. Heart failure, I highlighted here, is a recurrent challenge. But we wouldn't have known without an algorithm going through all the free text in the patient records down here that the patient records that contain in the free text of the chief complaint, fluid, the word fluid appearing is a bad sign for staying out of the hospital. And the algorithm has figured that out. And it's using all the information in the classifier you just saw. So this project has been very intensive. We built many, we'll say numerous predictive models for healthcare, including different kinds of discharge within different parameters. The emergency folks like to say, I want to predict if this patient will bounce back in 3 days with the same problem to the emergency department. Death within 30 days, inpatient discharge to inpatient again in 30 days, and then congestive heart failure. And also infection, hospital-based infection is a very common problem. To predict in advance that a patient will come down in the hospital with one of these nasty bugs, C. difficile, MRSA, and VRE. It's actually itself in the top 10 causes of death in the United States is hospital-associated infections, and very expensive. We also built new kinds of models. Remember the surprise model for traffic that I told you about? This is a surprise model for a confident physician. So what this is saying here, you can't read it, I'll just tell you in words here, is that this model was trained on data of the form and will predict patients of the form. This patient you're discharging right now from the emergency department will bounce back to the hospital in 3 days with a primary diagnosis nowhere on the current chart. Surprise. Oh, do you want to look at what I think what I think the patient will come back in 3 days with? You can peek now if you'd like, and you can imagine showing this to physicians. And so, again, you can imagine a confident physician not wanting to look at a system and so on, but imagine telling the physician, we have a system that will compute the likelihood that you've missed a diagnosis here, and even light up a flag when this likelihood goes high. And it's been fun working with the emergency department physicians on these kinds of models, and the patients that we see that have this particular composition per the outcome, and have them speculate, wow, what happened? That was out of the blue, or someone should have seen it a mile away was one of the classes of patient, and another one was, boy, I'm not sure how that happened, how we missed that one. And so you can imagine how this goes. It's a very interesting model to think more about these kinds of models in the real world. Not to tell us things we know, but to tell us things we likely don't know. So we actually, just so you know, back to the story unfolding here, we showed these models work well. We worked with our healthcare team, Microsoft Amalga product team, to actually build what's called Readmissions Manager for Amalga. And when you go to the real world, you face all these interesting challenges. For example, there's engineering challenges. Well, you guys had thousands of variables in your model. You could afford offline to run these big studies. We have real-time needs. We want to go over each patient in hospital every few minutes and update the probabilities for various predictive models. So we had to basically back off, and we look at these curves that I mentioned to you before, and let's look at how much do we lose by, let's say, going down from 500 features down to 37 features, for example, understanding the engineering trade-offs there. So we went live in June with the system, our first customer, and the system actually trains locally on data at local hospitals. And you see in this column here, I just highlighted here, the probability that those patients will bounce back. We're sorting by that right now. And to use these, we're now in the middle of watching how these systems work in the real world. In fact, not just that, but we actually the next phase of our work is saying it's not just about the probability, it's what do you do about it? And this is a whole deep analysis we've been engaged with, going from the predictions to the decisions. And in fact, one of the approaches we're very excited about is we can compute, given this training and test holdout data in a hospital setting, what's the expected value of this system being immersed in a legacy hospital, by doing a cost-benefit analysis on a holdout set, for example, given a decision to invest more in a patient who's at high risk for bouncing back to the hospital, such as a post-discharge special program, keeping them longer for observation, and so on. These are all decision analyses you can do dynamically, and you can then run the whole system and simulate what it would do in the hospital with a holdout set and get a sense for what we call the expected value of the overall system. I've always been very excited about this concept, by the way, of characterizing the true, genuine value of a computational solution that's sitting in a large, complex environment. I think that gets to the heart of, you might say, even sexier artificial intelligence projects. Why did this intelligence evolve? How can I make this robot better than that robot, and so on? This is an application in the healthcare space. So speaking of these more exotic applications, I wanted to start off with transportation and healthcare before I dove into richer applications that mesh together vision and speech, natural language. And this gets back to the area that I mentioned a bit earlier, integrative intelligence. We have a nice team in this space. So with work in this space, the idea is to mesh together natural language processing, NLP, motion control, speech generation, speech recognition, planning, learning, vision, and inferential methods. You might say that the goal here is in part to build comprehensive systems where the whole is somehow magically greater than the sum of the parts. This is kind of maybe a dream of AI, that if we bring together vision and speech and natural language and various kinds of reasoning and learning, that there'll be some synergies among these components if you weave them together in an effective manner. So our main project where we're exploring this integrative AI notion is called situated interaction. The idea is to have systems that can reason about teams in the physical world. Often you have multi-parties, not just a single user, for example, like a team of surgeons in a physical environment. Or I think maybe the first way you'll see situated interaction solutions in the world, 2 or 3 people in front of a billboard, and the billboard knows they're there and gets a sense for who they are. Is it a family, for example? Or someday you'll be pouring some, you'll have a situated interaction system in your kitchen, you'll be working on a recipe, and the system will say, you can go ahead and pour it now, but real slowly here, this is a problem. Have your actions being observed and having scaffolding being provided by an intelligent chef, for example. You know, and I always like this example, like you come home from the theater, and you were very confident during your stay, your date with your wife or husband, that the robot was taking care of the kids. Things are going just well. In fact, it was an educational set of goals that evening, and you knew that you'd get called if there was any trouble at home, or the neighbor would have been called. So it's not so scary. And this is the year 2039. And it's really just okay, and you have a really great robot, and it's fabulous with the kids. And so with that dream in mind, we think about what we might do. So one project we had is called the Receptionist Project. And what we did was, and I don't have my mouse here to click on these videos, so do I have a mouse?
No mouse, but trigger the video.
You'll trigger, it's going. Get some audio there too? Okay, so we put up cameras, several cameras with some disclaimers and signs in the entryway to Microsoft Research. This is our Building 99. And you're seeing the receptionist here. You're seeing some vision tracking, people ordering a shuttle, people have different tasks, and so on. We can move ahead to the next slide here, but the idea basically was, you think about the problem faced by a receptionist at a Microsoft building. People are coming up, someone wants a shuttle, more people are coming together. Some people seem like they're in a group. Maybe they need a single shuttle. Maybe they come here to visit somebody. And so we watched how receptionists handle the multiple tasks of a limited domain, but fairly complicated in terms of the humanity and the human understanding you would need to get through this well, do a good job with this. And this led to us thinking through componentry in terms of software and hardware we'd need to come up with even the basic competencies of seeing one or more people, engaging them, tracking goals of various kinds, listening and understanding where speech was coming from. And this led to our first prototype we called the Receptionist. And we're actually, believe it or not, getting ready. We're near ready to field this at one of our buildings for real. Not to take over all receptionist responsibilities, but to start with some key tasks like handling shuttles, for example, in a very natural way for not just single people, for groups of people. And we'll give you a sense for how this works. I'll show you a short piece of a video. I'm going to probably stop it before we get to the end, because I don't want to waste too much time on it. We started about 1.5 years ago when we first developed this system, because I want to show you people where we've taken this now. And once we let that roll. The red dot is the actual gaze of the good news is we have a little lower there coming onto the project.
That's great. That's great. On the situated interaction project?
On your project, on your team.
That's
her gaze, and you see we're looking at the
Hi, my name is Laura, and today I'm here
number
with
of properties.
Receptionist with shuttle reservations. What's your name?
I'm Dan, and this is Eric.
Watch on the right side now.
Nice to meet you. Do you need a shuttle?
Yes.
Which building are you going to?
I forget, where are we going?
I think it's building 9.
You sure?
Yes.
So, you're going to 9, right?
Yes.
And this is for both of you, right?
Yes.
I'm making a shuttle reservation for Building 9 for 2 people. In case you want to correct anything, say or press star over.
So the system's looking at attention.
Are you visiting someone?
Okay,
Yes.
so I think
I'll
everything
help
should be
you
all set.
register in just a moment.
Fabulous.
Okay.
I think we're set.
Okay.
Excuse me, sir.
Yes?
So the system is actually working with multiple parties. It actually, when that third person walked in, the system actually did this to that person and came back to us. So it said, I know you're here. And then it watched our attention. And so these things are very subtle issues to watch people's attention and understand that you can now look away and work with somebody else while people are talking, for example. We did a bunch of work on making the system better in terms of the nuances of how it deals with a group setting. We have actually a trivia game we created where the system plays a host of a trivia game and engages multiple people. Did a number of studies with people from the outside world coming in to help us. I'll give you a quick sense of how this works. Just run a little bit of this video, tiny bit of it.
Next question. Libya is the only country with a one-color flag. What color is it?
Let's say green.
Do you think same?
Yes.
That's right. So far you have one correct answer. Now on to the next question. In the USA, hospitals have a Red Cross. What sign do they use in the Arab world?
What's that a red cross? What's that they use in the Arab world?
Solid blue circle.
Is that correct?
No.
So what's the correct answer?
Red crescent moon.
Yes.
So just now, when that young man said yes, she just looked at him and raised her eyebrow. It was like, okay. And we have a view from the machine, but it's very interesting. All the nuances the system is looking at to understand the pacing and control. Even understanding someone's talking to themselves, not to the system, is this a challenge problem? We put this trivia system. Actually, it's up on our third floor right now, around the hall, by this coffee area. People walk by, and people will come over to the system and now play with this. And we watch them and record them with their permission. And it's very interesting to watch and see how this all goes. Lots of nice footage showing how people get engaged and so on. In this case, one person, I won't play the video now, but one person is playing and he gets a couple questions wrong. And the system says, I think you need a bit of help. Hang on a second. Hey, can you help this guy? And he joins in. It's very interesting to watch. So that work led to a really fun project where we get even deeper with the embedding of multiple components called the personal assistant. And this is by my door. And I actually use this. I rely upon this daily. And the idea is to now layer in multiple components, a number of which we've built on other projects over the years. In fact, several of these components were projects in themselves. For example, Coordinate. Since 2002, I've had the Coordinate server doing machine learning and reasoning about where I am and how long until I get there if I'm not there yet. It's fabulous. In fact, the system actually, this shows you a little, some of the inferences it's making at a particular moment. It's saying, well, I'm speaking right now in my office, but I'll probably end speaking in 6 minutes. I'll be home in a few hours. I'm still at work. I'm available on these channels here, and so on. I'm talking again. I'll be reading email in 3 minutes. It actually is very good with that. It's really funny how good it is when I get back to email again. So these inferences have been used by a number of projects we've had to do coordination among people and so on. It computes how busy I am at any moment. And that's one of several components running in the assistant. Now, let me just run this video to give you a sense for how the assistant works by my door, handling my scheduling and people coming to see me.
So who did the GMTK thing again?
Jeff would do that.
Okay. Oh, is Eric? He's not around.
Are you looking for Eric?
Yes.
Are you Dan and Paul?
Yes.
It's off the calendar.
I'm his virtual admin.
Okay.
I know he has a meeting scheduled with you, but he's late from his previous meeting in Building 34. He's no longer on his laptop, so I expect he'll be back in 10 minutes or so.
Okay.
You can go ahead and wait in his office if you'd like.
Oh, we'll come back in a minute.
Okay. I'll make sure to let him know when he returns.
All right, thanks.
See you soon.
So this is Jeff, right?
Jeff Bill.
Okay.
Hello,
Hi.
are you here looking for Eric?
Yes.
Eric is having an impromptu chat right now, but I expect it should be over in around 10 minutes. Would you like to wait for a bit?
Sure.
Sounds good. He shouldn't be too long. Guess I'll see you later then. Bye-bye.
Bye.
Hello,
Hey.
are you here looking for Eric?
Yes.
Are you here for the 2 o'clock meeting with Eric?
Yes.
Are you band labeling?
Yes, I am.
Great. Eric is expecting you. Will you be joining the meeting?
Yes.
All right. I'd let Eric know you'll be joining his meeting with Dan. If you don't mind waiting around for a few more minutes, I'm sure he'll invite you in shortly. Guess I'll see you later then. Bye-bye.
Bye-bye.
Bye.
So I'm going to move ahead, but there's several other scenarios here that are a lot of fun.
Hello. Are you here looking for Eric?
Yes.
Eric is busy working on a project at the moment.
So let's move ahead. You'll see in a second how the busyness is fabulous and it works quite well, and I'll show you about that. I'll talk about that in a second on a separate project. The system recognizes me when I walk up. It'll say, "Hi, Eric," and give me a quick lowdown of who came by and so on on the way into my office. I get email from the assistant. It's fabulous. So my comment is, if this is the kind of the ENIAC vacuum tube era for this kind of technology, in 20 years I can't imagine living without the system. I should say that it's not just those kinds of embedded applications by a door. If you can run this video, we have a 3rd-generation elevator project using the same platform you saw by my office. But now we're watching people in the lobby of Building 99, and we're ordering elevators for them so that when they get to the elevator, it's there. Or the doors stay open by themselves. I often tell people that it's so 20th century to have to stick your leg in a door to keep it open. It's like, can it see that this is what I want? In the Connect era, elevators should be very bright about that. And doors and trains and subways and so on. And this is going to be a major application, I think, just an ambient application. Our grandkids will see movies where people had to put their arm into elevator doors and they'll say, "What was that all about, Mom?" I'm sure of that, by the way. It would seem so odd. So just let me end with some directions before we go to question and answer. First of all, a big area that goes hand in hand with machine learning is visualization. A few years ago, we built a system called Notification Platform that would assign urgency scores, automatically learn to assign scores of how urgent something was to email, tasks, alerts, calendar items. And we said, well, how do I display all these? And we came up with a visualization called the Microsoft Research Scope. And the idea here is that for items along different dimensions here, email, calendar, tasks, the closer to the center of the scope, the more urgent. So you can sort of look at these, you can hover over these items and see what they are, and they get closer and closer to ground zero during the day if they're urgent, or they fade away if they're growing less urgent. So, but in more general, the point here is that not just particular visualization. It's often the case that we want to really inspect and understand the inferences from intelligences and such as machine learning and reasoning. And one way to communicate with people is through rich visualizations that are designed for people. Now, on that front, an area that we're kind of excited about, it captures a thematic area of research in our group that I mentioned at the introduction, we call complementary computing. The basic idea is this. You can look at 20th century cognitive psychology as largely defining people as very powerful intellects, but with very, very regular and characterizable deficits, you might say. Things that we don't do extremely well, like multitask, for example. And if you look at this little blob here as representing our abilities, where abilities and efficiencies of how we do tasks on the y-axis here, and these are well-known, well-characterized gaps, there's a kind of a dream that couldn't computational systems learn about not just about gaps across humanity, the human cognitive substrate, but even personalized gaps, and expand and extend our ability, augment our cognition. And we've had efforts in different areas of cog-psych, attention, judgment, memory, as separate projects that you can weave together someday. And we can talk about just a couple of them briefly, but there's a promise that sensing, learning, and reasoning will provide this kind of extension. Systems that really know minds well. One area we did a lot of research in, we sort of were leaders in the academic community in, can I figure out what's the cost of interruption of a user right now in a system through sensing, and given incoming important messages, some less important than others, understand how to manage alerts and information such that people could basically trade off the value of focus of attention with the cost of deferred processing of information, building triaging systems like that. And this is a little model here we built from training data of a system called Busybody that you train up during a training phase and then would watch you working on desktop or in your office and understand at any moment what's the cost of interrupting you. By the way, my personal assistant calls my personal busybody model. So at any moment it knows how much money I'd be willing to pay to avoid an interruption of type X. And it's great to be sitting in my office working at my desk and have that system calling this model. And I hear the system in the hallway saying, Eric's real busy right now. Can you come back in like 10 minutes? We'll try again. And I'm really rushing on a deadline. And then I'm done with it. And it says, you can go right in now. It's fine. And these models are, if you read our papers, are quite well calibrated to what people would call sense that they're too busy to be interrupted at any moment at a particular time. And they can run in the background as components you can add into software. Here's a system on the memory side that actually learns with machine learning what a landmark event is. So imagine training up models, which the system does, called Life Browser, that assigns a probability that any photo collection, any web browse, document on desktop, or appointment would be considered a landmark. And lets you search over, in my case, 20 years of information with a volume control of sorts that takes all your stuff, in this case my appointments for a segment of time, and shows you the most important ones, and then lets you slide a volume control to see more and more, and to search, do full text search against those landmarks. It's called Life Browser. Finally, mention another direction here is that many applications won't be so in your face as my assistant, for example. I heard the giggling like, yes, it's not so fluid yet, it's kind of stilted, and I'm not sure if I want a floating head by my door. Yeah, I mean, a lot of machine learning is going to be embedded into the infrastructure and background. For example, for everybody using Windows 7 laptops and Windows 8, if you're using the preview yet, you're using our machine learning code, which is doing something called Superfetch. So in the background, Superfetch is learning about the sequence in which you use applications by time of day and day of week, and it's learning to prefetch apps in the background that are likely to be launched next or soon with a cost-benefit analysis, given some available memory, so they're much snappier and even faster. And what's really fun about this project was we built the system and we wanted to test it, and we said, can we test the system now with beta users a few years back? And right away we said, okay, how well are we doing? They said, okay, well, here's 122 million app launches across users. How well are we doing? And we can see how well we're predicting from our swim data for volunteers using Windows 7. I'm not going to dwell long. We may have some time in the end to talk about machine learning and privacy issues. I think it's a very hot topic for us. We're moving in this area with seriousness. I'm very excited that there's much we can do in this space, not just grab everyone's data and have you click on a balloon that says we're now grabbing it all, thank you, goodbye. There's quite a bit we can do in this world. One area is called protected sensing personalization. Let me talk about that a little bit. So the idea basically is to say, imagine if data mining and analysis on your behalf took place in the sanctity of your own machine. So your own machine is getting GPS data. Your car knows about your GPS data. Nobody else does. And models are built that are then used on your behalf in real time, all within, again, the sanctity of your multiple machines. There are many applications where there's no reason to share your data with the world. And things work just fine. As an example, we have a project called Personalized Search, or P-Search, and the idea is the system analyzes your desktop completely, but it's all internal. No data is shared out anywhere. Your email, your documents, your web activity, we actually have a personalized result ranker. So when you go to do a search, like Lumiere, for example, which was a project at Microsoft Research, the search engine call goes out and brings back a whole bunch of search results, like 400. And then in the quietness and the privacy of your own client machine, resorts them based on its analysis of what you want, given really a close touch with your data. In this case, you can sort and bring up to the top what I'm looking for. Not Lumiere, the brothers in Paris, but Lumiere, the project. So let me stop there. I'll just say that, we'll take some questions and answers, that applications of this technology, sensing, learning, and reasoning, AI, it's very much in its infancy. I foresee unprecedented value to people and society. And at Microsoft Research, we typically pursue principles through applications. We love shipping products to get experience with them and enhancing people's lives. But we often get back to questions and principles again in a cycle like this. So I'll stop there and take your questions. Thanks very much.